modular construction. Okay. And so this is a topic that is becoming really popular in the Western United States, and in particularly pushing the limits of modular construction. We've kind of understood prefabricated construction for a while now, and I'm going to talk about the differences between the two. But we're really looking at the industry and thinking about how we can streamline the industry, streamline manufacturing, streamline construction, and decrease cost. And so the architecture, engineering, and constructions, or the AEC sector, is one of the largest in the world economy. So the field that we all work in takes up about 10% of the world economy. And so there's a lot of finances being exchanged. And so this industry employs a lot of people, and it creates a lot of companies, but we are quite inefficient in the way that we actually function. We've barely improved in our productivity since 1945. We're seeing a lot of improvement in manufacturing processes for airplanes, for cars, for a lot of the products that we use in our everyday. We've watched as we've become more efficient in developing technology. From seeing how the first smartphone cost thousands of dollars, and now you can get a smartphone for just a few $100s. We've really decreased cost in all these fields except for in the AEC industry. And so as a response to that, there's been a number of efforts in the last 10 years or so to try and disrupt our industry. And so we're kind of in this era of disruption right now. And I don't know how much as students you're aware of what's happening in our industry and new companies that are popping up, but there are a lot of new companies happening. And while all of them are not successful, they are challenging us, and they're challenging the way that we view this field. They're challenging the way that we are seeing the structure of our field. Normally, an owner will hire an architect, and the architect will then hire a structural engineer and a geotech engineer and a mechanical engineer to make sure that the building is built. And these are all from different companies. But back in 2015, 2016, a company named Katera popped up, and they said, well, why are we doing that? Why are we hiring all these different companies to then work together? What happens if we vertically integrated the building construction field? What if in one company we had architects, engineers, mechanical engineers? What if we owned the forests that we got the timber from? What if we had the contractors? What if we had the lumber industry? All within one company to begin to vertically integrate this. And they actually got startup money from the same people that funded that tried to vertically integrate the iPhone and reduce the cost of the iPhone. And while this company did fail, it's still being talked about today of how it disrupted the way that we think about construction, because it was trying to expedite and speed up construction, and trying to look at where do we have waste within our field, where do we have excess within our field that is unnecessary? Where are there miscommunications? Where are there issues with regards to inflation of cost because we're transferring money from one company to the next? And how can we begin to eliminate that? There's been other efforts kind of in line with Katera, and a lot of it is really in this mass timber industry, where there's a lot of companies that are are buying the plants and buying mass like CLT plants to create the CLT, but they're also doing the structural engineering to build the buildings and employing contractors to do that. So they're maybe not vertically integrating as far and wide as Katerra, but they really are thinking about where are those inefficiencies and how can, as an industry, we be more efficient and therefore reduce costs and increase the speed of construction. And this is not happening just in mass timber. AISC has an entire campaign on the need for speed, and it is all about increasing the speed of construction. And a lot of it is really looking into modularity. How can we do more offsite fabrication with the entire emergence of robotics in the field of AI? How can we integrate BIM more into our projects so that we can expedite shock drawing processes, and how can we build these buildings faster? And so this all started with Speed Core. I don't know how many of you are aware of this, but there are these two steel plates, and then there's concrete filled in between, and it can really improve the efficiency and improve decrease the time of construction, particularly for high-rise buildings. These buildings are beginning to go up around the West Coast. The most notable one is the Rainier Tower in Seattle. The steel plates are the formwork. And so, for a building that may have used reinforced concrete shear walls, now you don't have to take formwork off and move it up the building. You just have the formwork permanently in place. So, this is, our field is really examining itself and saying, not every building is a landmark building. Not every building is using all of the efforts of modern architecture. There are a lot of just regular buildings that are being constructed. And how can we actually use our advanced manufacturing techniques? How can we use our knowledge to increase the speed of construction, particularly for these buildings, because ultimately that's going to be more sustainable. And so, when we're thinking about streamlining our building manufacturing and assembly, our engineers, we as structural engineers are really at the forefront of this, because we can design for better constructability. As we begin to go into these novel systems, as we begin to push modern architecture, these are not particularly constructible buildings. So they become very difficult to actually construct, therefore decreasing the speed of construction, increasing the cost of construction, which is contributing to our housing crisis. We have a lot of manufacturing processes that have been expedited in this country using robotics and using a lot of advanced techniques. And so how can we take advantage of that? How can we do more off-site construction so that large pieces of the building are coming to the site already constructed and we can just put them into place? And then looking at the entire whole life of the building. For those of you who are going to go out into industry, the entire market sector of tenant improvement is huge for structural engineering. This market sector is for when one tenant moves out of a building, usually a business, and another tenant moves in. When that happens, the new tenant always needs a structural engineer, needs to hire a structural engineer because their configuration of the space is going to be different. They're going to want to hang different things at different points in the slab. They're going to want to core through slabs for different utilities. They're going to want to build out different portions. They're going to want to knock holes in walls. And we as structural engineers are going to have to adapt that space for that new tenant. So how can we start thinking ahead in our building design? How can we design for that as structural engineers, knowing that a tenant is not going to be in this space for the entire life cycle of the building, which could be 50 to 100 years? How can we actually think about the adaptability of the space so that every time a new tenant comes in, we are not doing more and more construction, which then adds to the carbon footprint of the building, adds time to a tenant moving in and out of the building, and makes it difficult for the building itself. And so, modular construction really comes into all of this. So we have, this is an answer to a lot of, designing for constructability, designing for manufacturing, and designing for adaptability. But it also is, a chance for us to build buildings quickly and efficiently, right? So I had mentioned, not all buildings are going to be these landmark modern buildings. And if we have a building that has this regular footprint and just regular floor plan every single floor, this could be a really great opportunity to use modular construction, because you are using this repeatable floor plan over and over again. And one place this can really help us is in our housing crisis. We have a huge housing crisis on the west coast of the United States. I'm in Oregon. Portland and the Pacific Northwest has one of the worst housing crises in the United States. And so, how can we actually think about using modular construction to address labor and housing shortages, to address rapid construction methods for post-disaster reconstruction? If there is an earthquake, a wildfire, a hurricane, a flood, you name the hazard, afterwards we are going to need really quickly constructed housing that is safe, that can resist aftershocks or subsequent hazard events. And we just went through a global pandemic and understood our hospital shortages and healthcare shortages. And so, during that time, how can we think about additional patient care facilities in these, not just in a post-COVID situation, but also in a post-disaster situation? If our hospitals are actually damaged, how do we think about, how do we provide additional patient care after a disaster, so that a community has access to healthcare, and then they can continue their operability and their functionality. And so the time savings that occurs during modular construction is really based on this, that you're performing the construction of the building off-site while the site itself is being prepped. So in traditional construction, which I'm showing on the bottom row, you are prepping your site and then you start building construction. But in modular construction, you're building in another location as you're prepping your site. So you're able to do multiple steps at once and therefore increase the speed of construction. And that time savings can reduce the schedule by about 30 to 50%. We're seeing that actually in low-rise modular buildings, we can decrease the cost of the building by about 25%. As compared to conventional construction. And most of that has to do with construction waste and time. And so you have crews working less hours. That means that you can actually decrease the cost of construction. You're not necessarily decreasing in material. And so I'm going to show you a video. This is about a minute. So right after COVID hit Wuhan, China, there was a hospital that was built, a 10-story hospital that was built within, or a hospital, not a 10-story hospital, a hospital that was built within about 10 days. And it was built using modular construction. You can begin to see all the modules and the layout here. And so I wanted to show you a time-lapse video of this because I think it's pretty incredible. When we think about construction in the United States, a lot of you are on university campuses. I'm sure you see buildings that are under construction for years. And then they build a building in 10 days. So, thinking about how we can actually increase the speed of construction and what is possible is kind of remarkable. Okay, so the music is kind of dramatic. But I mean, you know, I'm not saying that all hospitals need to be built in a time of 10 days, but I think it's what's incredible about this example is to show what is actually possible in our construction. That if we are able to use modular construction for certain applications, we are able to drastically increase construction, and how we could actually, you know, solve a lot of our societal problems through that increased speed of construction would be incredible. But it's not only used for for hospitals and for these emergency situations. There are a number of examples of modular buildings that have gone up all over the world, including, you know, here on the West Coast in high seismic regions. And so, you know, we are starting to see the use of modular construction for hotels, for apartments, for you know, commercial spaces, in order to rapidly build buildings, but also to try it out and see, you know, what is the possibility of this new construction. Okay, so moving on to, you know, I'm going to kind of give you an example of some work that we're doing at Oregon State University, and this is all around mass timber modular construction, and we've been working on mass timber panelized modular construction, as well as mass timber volumetric modular construction. But the reason you know, mass timber is really popular in this is that it's just inherently modular. So you're watching here as a CLT floor is being put into place. So when, you know, during mass timber construction, there's very little trucks on site. There are very little storage of material on site. The trucks are coming with the material itself. It's being picked off the truck. It's being put into place almost immediately. And so that in itself is modular. We're not pouring concrete on the floor. We're you know, putting these panels into place, and now we have a floor. So it's in itself modular in terms of kind of like flat packed modular. And there is a lot of offsite construction and manufacturing that's occurring. You know, the holes that you're seeing over on the right, these were most likely drilled or offsite in a shop. The connections themselves were CNC'd offsite, so that everything can be put into place. So there's very little work occurring, you know, on the site itself, other than putting everything into place. So, you know, the mass timber itself is really primed to be used in this volumetric modular construction. And so there's kind of two ways to think about modular construction in terms of volumetric modular construction. The first is basically like shipping crates being put into place. So you have these full-blown cubes that are being put into place and stacked upon one another, and they have walls and floors, and they're all made out of CLT. That type of construction is very helpful for low-rise buildings, and is being used throughout the country for low-rise building construction. But the project I'm about to show you that we've been working on at Oregon State University is focusing on high-rise building construction for modular construction. And so what that looks like is glulam beams and columns, as well as CLT floors. And so the modules themselves have 4 glulam columns with 8 glulam beams, you know, 4 per on the supporting the mass timber panel for the ceiling, and 4 supporting the mass timber panel for the floor. And these are connected together with kind of an interstitial space between the modules where all of the utilities are run. When you can imagine if these are all cubes, you need to punch holes in the walls in order to run utilities through the length of the building themselves. And so that can be problematic if you're using your mass timber walls as lateral systems. So in this type of configuration, there are two different types of connections. The first are the connections within the module themselves. This is an intra-module connection. And then you have the connection between the modules to connect the modules together to create either a diaphragm system or just to create continuity of load path. And that is called an InterModule connection. And I'm going to focus a lot the rest of the presentation on these intermodule connections that connect module to module, because the behavior of the entire building itself is going to be dependent upon this connection, the stiffness of this connection, how this connection is designed, and it's really the behavior of the whole building in a seismic event. Okay, so before I start though, I'm going to talk a little bit about what these big research challenges are with modular buildings. And so if we have this type of modular building looking at an elevation, we apply some lateral forces to it. First and foremost, we have to ask ourselves, where are the diaphragms? Are the diaphragms at the floor level? Do the ceilings themselves contribute to that diaphragm action in any capacity? We have to ask ourselves how the stiffness of the module to module connection or the intermodule connection influences the behavior of the building. How does the stiffness influence the drift, the interstory drifts of the building? How does it influence the diaphragm behavior? How does it influence the accelerations that we're seeing at each of the floor levels? And then lastly, can we use ductility and overstring factors for regular buildings? Can we take everything we know about the seismic performance of regular buildings and apply it to the seismic performance of modular buildings? And where can we not apply it? Where do we need to develop new knowledge? And where can we take that knowledge and transfer it over? And so I'm going to talk a bit about the first two questions because we haven't really begun answering even all of the second question in a project that we're doing at Oregon State University. And this is just one example of a project that is happening. There is modular construction research occurring, for low-rise buildings at Oregon State University as well. I'm going to be focusing on high-rise buildings. And there are a lot of companies throughout the Pacific Northwest that are looking at how to make this feasible, and really mainly focusing on this, the panelized kind of shipping crate construction for low-rise construction, because the knowledge is just not there yet for this high-rise construction and how we can actually, and what it looks like to actually have these intermodular connections, what they visually look like, as well as what kind of stiffnesses do we need to meet in order to get the global building behavior that we need to meet the building code. Okay, so I'm going to talk a little bit about the role of intermodular connections and the behavior of modular and mass timber buildings. Again, this is an ongoing project at Oregon State University. We're in the second of 5 years of this project. And I'm going to try to do the work of my graduate student justice. And I'm going to focus today on two points. The first being the placement of these intermodular connections. Where do we put them? Do we put them at the diaphragm level? Do we put them in the interstitial space? Does that even matter on the global behavior of the building of where we put these connections? And then looking at the stiffness of these connections and how that changes the behavior of the building. And so for this study, we looked at 3 different case study buildings, and it met the type 4A, type 4B, type 4C construction. And if you have no idea what the words that I'm saying, these are types of buildings out of the International Building Code. So the International Building Code has different types of construction that relate to the building height as well as the material that they're constructed out of. Type 1 and type 2 construction are typically steel and concrete buildings. They're typically non-combustible buildings. Type 4 buildings used to be one category of type 4 heavy timber building that was 9 stories or 85 feet tall. And with the emergence of the 2021 International Building Code, we saw the expansion of that into these type 4A, type 4B, and type 4C. So you can go all the way up to 18 stories in a mass timber building. That doesn't mean you can go up to 18 stories fully exposed in a mass timber building with no fire protection. As you increase in height, you need to add additional fire protection to the building, in terms of, you know, gypsum wall board, etc. But you can have a 9-story building that's almost all fully exposed in mass timber. And so we wanted these case study buildings to kind of match up with what is in the International Building Code. So throughout my results, I'm going to talk about the 18-story building, 12-story building, and the 9-story building, and this is why we chose those 3 buildings. The floor plan of each building looks like what I'm putting on the screen right here. This is a very similar floor plan to what the Brock Commons building is. That is an 18-story mass timber building with a reinforced concrete shear wall, two cores, similar to what I'm showing here. That is a University of British Columbia dorm. So perfect example of where you could probably use modular construction, where every single room is basically the same, and you have this very regular pattern of the floor layout from floor to floor to floor. So we used a very similar column grid and core location to kind of mimic that building. We designed these buildings to be located in Seattle, so high seismic region. They have the site class D, risk category 2. The CLT that's on the floor level is all a 5-ply CLT, spruce pine fir. And then because we actually found that that is where the diaphragm is, it is not at the ceiling level, and the ceiling doesn't really contribute very much to the structural performance, at least that CLT panel does not. But we do need a CLT panel there for stability during transportation. We used ponderosa pine for the CLT, a 3-ply ponderosa pine for that type of that CLT panel. The ponderosa pine is a product of forest restoration. So when you're doing wildfire mitigation throughout, particularly in the Pacific Northwest, we are removing a lot of ponderosa pine from the forest. And a question that we're having, we as an engineering community, is can we actually use that? It's a low grade lumber, but can we use it in some sort of capacity so we're not just throwing it in the garbage? And it turns out we can use it in CLT for certain applications, and we're kind of highlighting one of these applications here of where we could possibly use it. In this building, we used 10 pounds per square foot superimposed dead load on every single floor and 50 pounds per square foot live load on every single floor. And all of the building components were modeled using elastic uniaxial materials, and I'll get to the reasons for that in a little bit. Each of the individual modules can look like this, as I'm showing here, with dimensions, and these were designed for gravity loads as well as for seismic loads using the equivalent lateral force procedure, and then checked for forces using our open seas model. And so what the connections look like is that they are 2-node 0-length elements. So I'm not really showing them as 0 length here, but they are 0 length. And so we looked at what happens when we actually put the connection at the diaphragm level. So this is when the connection's at the floor beam and diaphragm level. And then what happens when we put them in the interstitial space? What happens when we put that connection at the intersection of the columns itself? And how does that influence the global behavior of the building, right? So if we're going to design these module to module connections, where do we put the connection? And how do we choose that location such that we're minimizing forces in the connection, we're efficiently designing the building such that we're using less material than we have to? Each module itself was designed and modeled such that each individual diaphragm in the module was assigned a rigid diaphragm constraint. But then we looked at what would happen to the full floor diaphragm by putting the two node link elements at these different locations, and then by also changing that translational degree of freedom stiffness, how does that change the definition of the diaphragm itself in terms of rigid, semi-rigid, or flexible? Okay, so what we found, I'm going to go over through some of the results. First and foremost, we found that there are smaller interstory drifts. So when we actually put the connection at the floor beam level, at that diaphragm level, we saw that there are less interstory drifts than at that intersection of where the columns meet one another. We also saw that the location of the maximum interstory drift changed. When the connection was at the diaphragm level, we saw the maximum interstory drift located at about 80% of the height of the building. Whereas when we put that connection at that column to column location where the columns are connecting together in the interstitial space, we saw that the maximum interstory drift actually occurred at about 60% of the height of the building. And this we saw regardless of where we put the connection, as well as what height of the building. So on the left is the 9-story building, and the middle is the 12-story building, and on the right is the 18-story building. The gray lines are when the intermodule connection is located at the column-to-column joint in the interstitial space, and the gray and the black lines are when the intermodule connection is located at the diaphragm level. So we see a very large, pronounced difference in these shorter buildings. We're less difference in the 18-story building, but also you know, what was interesting is that actually we see a difference in the location of where these maximum drifts occur throughout the height of the building. In all of the buildings, all of the you know, interstory drifts were below 1.5%. So they definitely met code requirements. And our reinforced concrete shear walls were actually designed to limit the drift of the building. But you know, we are beginning to see that actually, you know, intermodular connections and the location of them can actually influence the global behavior of the building. Okay, so if we want to begin to start changing the stiffness of the building, of the intermodular connection, sorry. So as we begin to decrease the stiffness of this building, we begin to increase the diaphragm deflection, which would make sense. We begin to see that the floor level begins to behave more like a flexible diaphragm as we begin to decrease the translational stiffness of these connections. And that's regardless of where we put these connections, whether we put the connections in that interstitial space between the two column locations, or if we put them at the diaphragm level. And so we're putting here on the x-axis is the diaphragm deflection. Here are these vertical lines are the cutoff points for the diaphragm deflection for rigid, semi-rigid, and flexible definitions. We also filled in dots are when the connection is at the diaphragm level, and then the open dots are when the connection is in the interstitial space. So regardless of the you know, location of the connection, we're seeing that as we begin to decrease that stiffness, we're increasing our diaphragm deflection, regardless of the location of the connection and regardless of the height of the building itself. And so as we continue to look at different metrics, we're also seeing that we looked at, you know, well, what happens if we look at, you know, the rotational stiffness, if we change that, and we really don't see much difference if we are changing the rotational stiffness here. What I'm showing you here is pinned versus fixed rotational stiffness. And so allowing, you know, infinite rotation versus allowing no rotation. And we can see that the lines are pretty much the same. We don't see as much of a difference between these two as we might in some of the other in some of the other plots that I've shown you here, where we've seen a large impact on the behavior of the building. So just in general, we just continue to see that as we are decreasing that translational stiffness of the connection, we are increasing the diaphragm deflection, and the diaphragm is becoming and behaving more like a flexible diaphragm. Okay, the last parameter that I'm going to talk about really is the structure period, and how that translational stiffness is influencing the structure period. And so again, the filled dots are when the connection is located at the diaphragm level. The open dots are when the connection is located at the column-to-column connection in that interstitial space. And again, we see the same behavior that we've been seeing, similarly in other plots. As we are decreasing that translational stiffness, we're increasing diaphragm deflection. We're also increasing the period of the structure. So, again, like thinking about holistically, like how are we designing this building? Do we want the building to have a short period? We're seeing less of a pronounced difference, in this 18-story building because, it's an 18-story building, but in these low-rise buildings, we're going to see more of an impact of that translational stiffness on the global behavior of the building. How do we want our diaphragms to behave? Do we want them to be behaving more like flexible diaphragms? Do we want that to have a longer period to get out of that plateau phase and have less seismic demands on the structure itself? So intentionally designing our building and carrying that through into our module to module connections, so that we can use our materials intentionally and efficiently. So just to summarize some of the conclusions that we found that decreasing the translational degree of freedom in the intermodule connections is going to increase the diaphragm deflection in the building period, regardless of where we put the connection and regardless of the height of the building. We found that the rotational degree of freedom of the intermodule connection has very little impact on the global behavior of the building. And the building performed better. We saw a better building performance when that intermodule connection was located at the diaphragm level rather than in the interstitial space at the column joints. And the reason we actually looked at that interstitial space is that's where steel module connections are located, and how everything connects together. So we were really basing things off of that steel building performance. But what we're finding is maybe that's not really the location that the connection needs to occur at. Maybe it needs to happen, closer to the diaphragm, and really we just have kind of simple column-to-column connections that ensure continuity of load path. And so I want to express extreme gratitude to the graduate research assistant who is on this project and did all of this work. I think he's on the call today, so hopefully I didn't get anything too wrong. And this research is funded by the National Science Foundation, so thank you to them as well. And I'm happy to answer any questions.
Thank you, Dr. Fischer, for such a wonderful presentation. And yeah, with the mass timber construction gaining momentum, I think this was a perfect fit and really a value addition for all of us. I think we have some questions in the comment box. So the first one is, does the for the video you showed for the China construction, I think it's regarding this, does the 10-day construction include the pouring of concrete foundations?
I don't think it did. I think that I think that it was just the superstructure.
Regarding the presentation, like the video recording and presentations, we'll if it's someone asks if it's okay to share the presentation online.
Yeah, so you're video recording this.
Yeah.
Right.
So
yeah.
So we'll definitely be sharing it with everybody. Then
yeah.
Recording. Yeah.
And there's a conference paper coming out for the World Conference on Timber Engineering. And so I can provide you with the citation and link to that. Maybe I'll like add it to like the end of the presentation, so that if you're going to like post slides, so that people can just go read the whole paper and get a lot more information. There was only so much I could fit into.
Yeah, I think that would be really great and knowledge enhancing for everyone. Any other questions by please feel free to unmute yourself and ask the question if you have any questions at this point. I see. I had one question regarding the, I mean, because since nobody's like people are thinking over their questions right now, regarding the Katera fiasco. If we were to provide a new company, say $2 billion right now, what would be the right direction according to you?
Oh gosh,
Yeah.
That's a big question. So I wouldn't think of Katera as a fiasco. I think this was honestly the first time that's ever happened. And it caused a lot of consternation to our industry. People and companies were very upset and very nervous about it. And it was really interesting to watch. And I don't think we've ever had disruption like that before, like very large disruption where a company starts, they have a ton of money, they're hiring all the best people, they're poaching people from architecture firms, from structural engineering firms, from contracting firms. Firms are getting really nervous. I think that it's good. I think it's good for us. I think that like it was really interesting. It made us think about things. Made us think about employee retention. It made us also think about, like, are we actually doing things in the right way? And because of that, like Katera was focused a lot on modular as well. There are, I mean, I can name like 6 modular construction companies in the Pacific Northwest or in California right now. And they all stemmed out of people who worked at Katera. So I think that the ideas and the like passion for it lives on, even though like the company itself maybe wasn't the most efficient at management or use of resources. So, I think that I think this topic is really exciting right now. And there's a lot of companies going after very big amounts of money, particularly in California, that are being supported by the lumber industry, by Cal Fire, by all sorts of different types of companies and organizations that are really pushing this like net zero sustainable building design. I just think it's a really exciting time because I think for like the first time, building performance objectives are not structural. It's sustainability. It's like functional recovery. It's like cost, speed of construction. It's all this other stuff that is making us as engineers think about our work in a different way. And I think that's really exciting.
Yeah, thank you so much. And yeah, it's really interesting that as you mentioned, we are trying to focus on things that we have never learned before as students.
Yeah. So as students, you're taking like structural mechanics and dynamics and seismic design, but then when you go out to work in industry, you have to think about constructability, manufacturing. You have to think about how people use the space. And as engineers, like we're not so good with people. So
yeah. 。 Any other questions by the
Yes,
audience?
I have one question.
Yep.
Thank you for the presentation. What kind of intermodular connection would you suggest as a typical connection?
So right now we are starting to design some because they don't exist for mass timber at all. No one's ever built modular mass timber buildings in this way. But in steel, what they tend to use, like HSS sections for the columns. And so they like use these kind of like buckets. So you put this, like the steel section kind of like fits into the bucket, and then you bolt it or weld it into place, depending on the amount of stiffness that you need for that connection. Hopefully that answered your question.
Thank you so much. Do we need to connect a connection for the uplift, or do we need to add some things to prevent uplift, or we can use it as uplift-free connection?
It depends on your building design. If you're going to have uplift, these like your, I think so. These are all in your gravity system. So it just depends on what your design forces and design demands are. You might need, if you're designing for a potential, like I think it just depends on what you need. We aren't particularly thinking about uplift right now in our designs. We're thinking more about continuity of gravity demands, and then also developing diaphragm action across the modules.
Just last question.
Sure.
Do you have any experience with steel modular building with a kind of bracing, steel bracing?
I have not worked with steel modular buildings. What our goal is we're examining the behavior of modular buildings, mass timber modular buildings, using reinforced concrete shear walls and steel brace frames.
Thank you so much.
Any other? Yeah,
sorry.
go ahead, Max. Go ahead.
I had a quick question of like, how do like on-site conditions affect the module construction? So if you have like, do they take into account what's already on site and then design for it, or do they have a kind of a pre-designed modular like building they want? Because I was thinking if they could have like kind of already pre-designed disaster relief buildings like hospitals or temporary housings, like if that's just like you could plot those anywhere, or do you have to take into account like what you're dealing with on site?
Yeah, that's a good question. For like post-disaster work, the research, and that's like another project that I've been involved in. The research is to consider to consider it like site independent, but also to consider what potential hazards could occur on the site. So very often we put people, after an earthquake, we put them in temporary shelters, and those temporary shelters last for years. So how do we design, temporary housing or temporary shelters that can withstand potential aftershocks? That or potential like hazards itself, high wind events or flooding or something like that. So that's definitely something is to consider. What potential conditions that structure would be exposed to as kind of like a quote unquote temporary, like 2 years may not be that temporary. But right now they, a lot of the post-disaster shelters are, like trailers, and they're not particularly considering those conditions.
Do you know like how long it would take to kind of assess those conditions to like, because ideally you'd want to get those post-disaster shelters out as soon as possible. Do you know like how long that might take?
Yeah, so like we imagine that like, states would have their own, kind of stockpile flat packed, post-disaster shelters that were, pre-designed for a potential hazard in that state. So, if we're using it in Oregon, then it could be, designed for, an aftershock or, a high wind event. And, it's like kind of disasters that you would potentially design for here. Yeah.
Cool, thank you very much.
Yeah, and so that's like a whole nother like area thinking about. So like we did some testing and numerical modeling of flat packed post-disaster shelters. And so like normally you might want so it's like thinking about like where do you want the failure to occur. So in those types of structures, looking at the connections of the panels together, we actually wanted the failure to occur in the screws in a potential aftershock rather than in the CLT panel, because that's what we want to reuse every single time. So like how does your design potentially change and your limit states that you're looking for change based on reusability and deconstruction. And so that's a kind of a whole other interesting topic.
Yeah, thank you so much, Professor. Also, we had 10 Uber Eats vouchers to give away to the students who have joined our seminar today. So I'll hand over to Max to announce the winners.
Yeah. Could you let me share screens real quick to show?
Yeah, I think you should be able to.
Everyone see that?
Yep.
So here, everyone highlighting green here are our Uber Eats winners. Congratulations, everyone. Aditya will send you an email later or right after this with your voucher, if I'm correct.
Yep, I'll be sending over the vouchers. Yeah.
Yeah. Yeah. Congratulations, everyone.
Yeah.
That's it for me.
All right then. Thank you everyone for joining for today's seminar. And thank you, Professor Fischer, for giving such a wonderful presentation. And I'm sure everybody had something valuable to get out of the seminar. And we look forward to seeing everybody in our future events. And thank you so much.
Thank you.